Okay, here's the second part of Lecture 2, and this has to do with inverse functions. So let's start by talking a little bit about what that means, and I want to use as an example the function 2 to the x. So 2 to the x, of course, we've been talking about it, and it looks like this. Asymptotic on the left to the x-axis, and goes through the point 0, 1, and then grows exponentially. And there's keys on calculators that allow you to compute values of 2 to the x, although most of them are random or just an arbitrary base. But let's suppose that you had a calculator key that actually computed 2 to the x, and you typed in this number like 1.20751, and then you hit this 2 to the x button, and out comes this number, whatever it is, and then you say, oh, I didn't mean to do that. I didn't mean to hit the 2 to the x. And I forgot what the original number was that I typed in, so you don't remember this. How do you get it back? Well, that's what an inverse function would do. If you had an inverse function, an undo for the 2 to the x, then that would get you back to the original x that you typed in. Well, it turns out that the 2 to the x function does have an undo, and that is the logarithm base 2 of x. This function is the function that would undo the action of 2 to the x. So if you typed in 1.20751 and then you hit the 2 to the x button, you would get back to 1.20751 by hitting the log base 2 of x button, if your calculator had one of those buttons on it. Actually, you can try this yourself. And almost all calculators have a log base 10 button or a natural log button. Natural log is log base e. We'll talk about e in just a minute. But you can calculate e to the x on most scientific calculators. Just pick a random number for x, anything, hit your e to the x button, and then hit the natural log of x button. And you should end up right back where you started from. Same thing for log base 10. If you start with 10 to the x and then hit log base 10 of that, you end up back with the number that you started with. And it doesn't matter which one you do first. You have to type in the number, hit the log button, then hit the 10 to the x button. Okay, so that's the basic idea behind the inverse function. There's a nice graphical interpretation of this too. And rather than try to explain it all, let's just remember, you probably saw an explanation of it at some point in your life, but the graph of all the log functions will look like this. They're asymptotic to the y-axis instead of the x-axis, and they grow rather slowly, as opposed to the exponential functions, which are asymptotic to the x-axis and grow rather rapidly. But if you compare the graph of, say, 2 to the x with the graph of log base 2 of x, you would find that they are symmetric with respect to the diagonal y equals x. So they're mirror images over that diagonal. So if you just reflected one, you would get the other. Okay, that's nice to know, but what good is that going to be for us? Well, occasionally it'll be handy, but the most important thing right now that I'm telling you is the shape of every log function is this. It's asymptotic to the y-axis, never touches it, gets arbitrarily close the closer you get to 0, and grows but tapers off and becomes very, very slow. By the way, you'll notice that there are no y values on this side at all. So what that means is that the domain of the log, let's say this is log base 2 of x, the domain of any log function is x must be strictly greater than 0. So you're not allowed to plug in any negative numbers. And that corresponds actually to the picture that you have up here with the exponential function, because with the exponential function, the y values, if you think of these as y values, there are no negatives. Below the x-axis, there's nothing. No y values are negative. So the exponential function stays positive, and the inverse of the exponential function requires positive numbers. And if you think about that enough, it makes perfect sense, because you can't feed in to the log function any negative number, because you can't get any negative number out of an exponential function. So it all works. Okay, so what about actually computing some of these things? So let's look at some examples that you've seen sort of before, and we'll get at the actual definition of a logarithm here. So let's try log base 2 of something like 8. All right. the understanding of logarithms that I got it from high school, and I didn't get it from a math person. I got it from a chemistry lab assistant who told us that logarithm means exponent. And so what this is, whenever you see the word log, you've got to think exponent. So if you don't know what this is and you call it y, then this is an exponent. Y is an exponent. So it's the exponent of what? It's got to be the exponent of 2, because 2 is the base. So 2 to the y is what we're talking about, and the only other number that's around is 8. So in this equation, most of you can figure out that the only thing y can be is 3, because 2 to the third power is 8. So in fact, the log base 2 of 8 is 3. And this gives us a lot of things, but in particular it gives us a definition of what log base b of x means. Log base b of x equals y, let's say. This is a sentence that we could read in English, and we could read it in English as saying the exponent, where the base is b, is, that's equals, y. The exponent, where the base is b, is y. Now, to put that in exponential form, you would say b, and the exponent is y. And what's that got to give you? Well, it's got to give you what's left, x. So anytime you have a logarithmic expression, you can unwind it like this to turn it into an exponential expression. So base is the exponent. The exponent, base b, is the exponent. The exponent is y. So log base b of x equals y means b to the y equals x. So here you can check your answer. Is log base 2 of 8 equal to 3? Well, because 2 to the third is 8, yeah. There are other examples. Just take one for another one real quickly. Log base 10 of 10,000. What would that be? Well, that would be an exponent. The exponent base 10, that would give you 1,000. So it's like saying 10 to what power? What do you put in the box there so that the answer will be 10,000? The exponent of 10, that would give you 10,000. Well, the exponent of 3 would give you 1,000. The exponent of 4 then would give you 10 times as much, so that would be 10,000. 10 to the fourth is 10,000, so 4 is the log base 10 of 10,000. Some other little things with this log business that are important to notice, and very, very simple if you look at them just right. This kind of drives people crazy sometimes. What would the log base 2 of 2 to the x be? And this turns out to be kind of the stupidest question in the whole world. If you don't know what it is, call it y. But what this says in English, if you read it, it says the exponent, that's what logarithm means, the exponent, where the base is 2, is y. The exponent, where the base is 2, is y, and the answer would be 2 to the x. So the exponent, where the base is 2, is y, would be 2 to the x. Well, the only thing y can be is x. So if you unwind it the way we did with the definition a minute ago, let me show you that again. Here was the definition right here. So the log base b of x equals y means b to the y equals x. So base to the answer equals x, b to the y equals x, okay? So hold that thought, and then look at this. 2 to the y equals that. And guess what? It's y. Now why is this such a stupid thing? Because remember where we started? The logarithm is the inverse of the exponential function. And what are we doing here? We're taking the exponential function and then hitting it with the inverse. So it's the undo of the 2 to the x. And so the answer has to be back at x again. So even though we called it y, now we know what it really is. It's whatever you started with. So log base 2 of 2 to the 5 has to be 5. Log base 2 of 2 to the 17.4 is going to be 17.4. It brings you back to where you started from. And it works the other way around too. If you take 2 to the log base 2 of x, that will undo the log. And these formulas are extremely handy, and we will use those a little bit later when we start talking about calculus and calculating derivatives of exponential functions and logarithmic functions. So we've got to be able to do this kind of dance back and forth with logarithms. Okay. While we're talking about logarithms, it's a good thing to look at the laws of logarithms. We looked at the laws of exponents, and it turns out that the laws of exponents and the laws of logarithms are really the same thing in disguise. We're not going to look at all of them, but we will look at the ones that are most important. And the first of those is the log of x times y. And the law that you should remember from this is that if you take the log, and it doesn't matter what base it is, log base b of any product, x times y, is the log base b of the first number plus the log base b of the second number. And this is again getting at the idea that logarithms, like exponents, work well with multiplication. So this is saying, if you read it in English, it's really nice. It says the exponent, base b, that you get for a product is the sum of the logs, the exponents. The exponent of a product is the sum of the exponents. And that should remind you of something. It should remind you exactly of the law of exponents that said that if you take two numbers to the same base, b to the x times b to the y, you get to add the exponents. So this law of logarithms is really nothing more than one of the laws of exponents in disguise. Now, just like people mess up the laws of exponents, they mess up the laws of logarithms even more. And just remember, logarithms, just like exponents, because logarithms are exponents, logarithms do not play nice with addition. So just like exponents don't distribute over addition, neither do logarithms. You're going to have log base b of x plus y, that's going to come up a lot, and you're just stuck with it. Now, if you could factor x plus y, then you could make x plus y look like a product of two things, then you could split it. But as the log of x plus y, you're kind of stuck with that. Do not try to write this as the log of x and the log of y in any way, shape, or form. Okay, logarithms play nice with multiplication. They also play nice with division. So you can go log base b of x over y, and that's going to give you the log base b of x minus the log base b of y. So if you take the log of a quotient, of a division, then you can subtract. Don't confuse this, though, with the log of x divided by the log of y. Here you're dividing two logs. That's not the same thing as taking the log of a quotient, right? Here you are taking the log of a multiplication or a division. And here you're dividing two logs, just like you could be trying to multiply two logs, log of x and the log of y. And if you multiply these two guys together, there's nothing good that you can do with that. You're stuck with that, just like you're stuck with log of x plus y. So, with log of x and divided by the log of y, we can't do anything. But log of x over y, we can. And the best is yet to come. This one is super, super important. The log base b of x to the y power. Logarithms work well with multiplication and addition, but they work wonderfully with exponentiation, because here they just knock the exponent down. So y as an exponent becomes a multiplier times the log base b of x. So you think of using logarithms to kill exponential expressions. That should make sense, because after all, logarithms are in some sense inverses of exponential expressions. And all exponential functions look alike, so logs should have a nice behavior with exponential functions if you do a log on top of an exponent. And so that's what's happening here. You're knocking down the exponent with the log. And this rule of exponents, this law of logarithms, is super important. We will use it so many times. And let's just do one simple example of that. Suppose you have an equation like 2 to the x plus 3 equals 7. So the question is, how do you solve that equation? You see, the problem is the x is up here in the exponent. I can't just divide by 2 because that's still going to leave me with an exponent up the x in the exponent. How do I get the x plus 3 out of the exponent? The answer is use the log. Use a log of any base. So let's just use log base e. I'll talk about this in just a second, but natural log, ln of x, means log base e. And we'll talk about what that means, what e is in a second. But natural log, you can take the natural log of both sides. So after all, if 2 to the x plus 3 is supposed to be equal to 7, then the natural log of 2 to the x plus 3 had better be the natural log of 7. But the beauty of this is that logs applied to exponents, exponential expressions, make the exponents come down. So that x plus 3 comes down and becomes a multiplier of the log of what's left is just 2. Now, the log of 2 and the log of 7 are constants. These are things that you can just calculate on your calculator. I don't know what they are, but I can give you an approximation for them, but that's not important. What's important is that any calculator can compute this, any calculator can compute that. You know, it's like 1, 3, whatever it is, it's a number. And so I can push this number around and move it to the other side. And so we end up with x plus 3 equals log of 7 divided by log of 2. And now you can see what's coming next. I divide those numbers on a calculator and subtract 3 from it, and then x equals log 7 over log 2 minus 3. And whatever that turns out to be, that's my answer. Now, it's worth talking about e for just a moment. We already talked about it when we talked about the exponential function e to the x. E is approximately 2.7, in case you've forgotten. And it's important to remember that much right now. We're going to spend a lot of time talking about e in the future and the function e to the x and the inverse of e to the x, which is the natural log. So these two functions are anti-functions for one another. They kill each other off. So if you take an exponential function base e and hit it with the log, you're back to x. If you start with x, do a log, natural log, and do e to the x on top of that, you're back at x. They undo each other. These two functions have got to become your best friends, and you'll see why in just a little while. If you have one of these to deal with, life is good. If you're dealing with 2 to the x, it's not quite so good. If you're doing log base 2, that's not so good either. These guys are the easy ones. Okay, let's do one more kind of problem, and then that'll be it for this discussion of inverse functions, at least for now. We are going to come back and look at inverse functions in the calculus in just a little while. But for now, let's just solve the problem of finding an inverse function for other kinds of problems. So here's the problem. Find f inverse. Oh yeah, well, this is how we call the inverse function. So this is the function that undoes f of x. So we're looking to undo f of x. Now, we already know what f inverse is if f is e to the x. F inverse would be natural log of x. So these two functions would then be anti-functions. They undo each other. But what if f of x is something like this? 4x minus 1 over 2x plus 3. What in the world would undo that? Now before we get something complicated, let's do put this aside for a minute. And I guess we'll do it on a separate sheet of paper. So here's a different question. Simple question. Suppose that f of x is 2x plus 3. All right? Then the question is, what's f inverse of x? And we're going to answer that question just from common sense. And here's the thing. What's this function do to x? So let's do a kind of a diagram of that. What does this function do to x? The first thing that you're doing to x is you're doubling it. And then you add 3. Okay? So you can think of a stupid magic trick here. Get some really dumb friend of yours to think of a number and tell him to double it and add 3. Now, you got to undo that. So what would you do to undo that? Well, the first thing you would do is subtract 3 from the answer that they give you, and then cut that in half, and lo and behold, you're back to where you started from. So here's the stupid magic trick for your friend. You tell your friend to think of a number. Suppose they think of 17. And then you tell them to double it, and they don't tell you what 17 is, so they're hiding that. They don't tell you what you get when you double it, 34, and you add 3 and you get 37. But they tell you 37. And then you go into this mental Karnak sort of mystical approach, mystical meditation trance, and then but really what you're doing is you subtract 3 from 37 and you get 34, and you divide that by 2, cut it in half, you get 17. You say, your number is 17. Bingo, you got it. And the idiot is astonished. Well, that's all it takes to undo a function when it's really, really easy. Okay. Unfortunately, in life, functions are not so easy. We'll be doing a lab later where we use the computer to help us calculate the inverse of a function. But for something like this, we need to understand how to do it. So here's the technique, here's the algorithm, to use the fancy term. We call this thing y because y is a y value for this function, but we want to know what is the function that will undo it, just like we calculated the function that undid 2x plus 3, which is the function that subtracts 3 and divides by 2. So what would the function be in this case? Well, the solution is to first take this equation, step 1, solve for x in the equation function equals y. Never mind how we're going to do that. After we do that, step 2, switch x and y. And so you'll end up with a y equals blah, 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 after you've switched x and y, because when you solve for x, this leads to an equation that looks like x equals blah, 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 right? If you solve for x, you'll know x equals blah, blah, blah. When you switch x and y, it becomes y equals. And this stuff is the inverse. So let's see how that works in this case. Actually, let's do it in the really simple case, the example that I had a minute ago, and then we'll come back and do this one. So back to the other page. Remember the technique? We just take y equals 2x plus 3. Solve that for x. So we go y minus 3 equals 2x. Divide both sides by 2, so x equals y minus 3 over 2. Switch x and y, so we get y equals x minus 3 over 2. This would be the inverse function of the original one that was y equals 2x plus 3. Okay? So that's the function that undoes the other one. These two undo each other. Takes an x, multiply by 2 and add 3, then undo it by subtracting 3 and divide by 2. That's how it works. Okay, so let's do the problem now where it's a bit more complicated. So what we're going to do is, starting with 4x minus 1 over 2x plus 3 equals y, and we'll just do some algebra. 4x minus 1 over 2x plus 3 equals y. I need to get the x's all by themselves. I don't like fractions any more than anybody else does, so we multiply both sides by 2x plus 3 to kill the fraction. So 2x plus 3 gets multiplied by y. I'll need to get the x's all by themselves, so I need to distribute the y. So I have 4x minus 1 equals 2xy plus 3y. Bring the 2xy to the left, bring the minus 1 to the right. So we're going to have 4x minus 2xy equals 3y minus 1, plus 1, excuse me. Minus 1 goes to the other side and becomes plus 1. And then we can factor the x. So x gets multiplied by 4 minus 2y, and that gives us 3y plus 1. And now we can divide both sides by this mess and get x all by itself. X equals 3y plus 1 over 4 minus 2y. And final answer, you switch x and y. Y equals 3x plus 1 over 4 minus 2x. Ta-da! And there you have it. Okay, so that's the end of the second lecture. We will see you in class.